Ha. Perfectly fine. We make it all work. And here are actually my slides. Yeah? I handed them in a week ago, and now they suddenly pop up. It's a bit like after a long flight, you know, with a connecting flight, and you see your baggage. It's on the belt. It's okay. So, apropos, while talking about flying, I thought I'd take some pictures of airplanes with me here, because I thought maybe, given my profession, someone would be disappointed not to see airplanes. What do you think? Which one has a better performance? Any? Yeah? Who thinks this one? Okay, a few. Who think this one? Hey, more. Yes, we're technicians here. And you have probably seen that this design there is much, much older. It's actually from the 1840s. It has actually indeed flown in a lab, so in a kind of hangar, a few meters and so on, but it's a steam airplane, yeah? So because in the 1840s they only had steam power, and they thought, hey, we power everything now with steam, and this was the airplane resulting. This is just someone's painting, yeah? But in a lab it was kind of working, yeah? Kind of. Never got really in the air. While this one is a Santos Dumont design, 1909, the Demoiselle, already kind of recreational airplane, flying something like 30 minutes, 100 kilometers per hour, being able to have one passenger. And there's quite a bit between this imagination, I think there's a laser in it, between the imagination and the real airplane, roughly something like 60 years. And then it took a bit more time until we were there. And I guess no one from these early times would have ever guessed an airplane would look like that at some point in time. And the big question is then, of course, yeah, where we are with airplanes looking like that, what is the next big step? And up to now here, there's a lot of new technology, new materials, fly-by-wire, and so on, yeah, inside. Everything with computations, needing computations. So we're depending on computations, and so it's kind of logical to look at what's the next big thing there. And there the idea was it could be quantum computing. Just to notion aside, yeah, Airbus today is a bit more than just airplanes. Yeah, we also have helicopters, and we even have satellites. And I just mentioned that because it becomes important in a moment. Here. And in order to find out about that a bit, we joined an EU-funded project, something like almost 3 years ago, called Equality. It had this, so I was joining later, so I can say that. I found that logo quite genius, to put the I inside there, with a lot of partners, and partners that are not only industry, but academia, and this is super important. And the idea of that project basically was, okay, we're looking a lot in hardware, at least this was 3 years ago. Now I had a lot of talks here, and I'm very happy to hear the direction is also going different, but what's about the software? And because we can have really good hardware, and we have already quite good hardware, yeah, but what do we do with it in the end when it is there? And we were assuming, hey, it's probably coming at some point in time. And you know, for aviation, the development spans and so are quite large. You put quite a bunch of ideas before you develop a new airplane. So we can think about that one as well. How do we use it when it is there? And, oops. Okay, one slide got missing. And what we have here are, of course, yeah, a lot of different areas we are looking at. Quantum simulation, we had a lot of discussions on that today. We also have use cases of that in Equality, just not so much aerospace related, which is why I don't have them, but optimization. And optimization, I can tell you, I have a lot of problems on my desk where engineers come to me and say, hey, I have that optimization problem, can you help me? Yeah, and so I just heard talks here where I would like to come back to at a later point in time. Here, it is the notion that we have some optimization problems. If we achieve only to get a little bit better, the result would be huge, yeah, in terms of Yeah? So one of the problems we have here, we're also running satellites. And these satellites usually have a purpose. They typically want to see something from space. And they have a path, and they can turn in a little bit to photograph different parts of the world. And then we have customers who say, I want to see something on the ground. Can be for agriculture, can be there are a lot of applications where this is required. And then we have to turn the satellites. And now the question is, we would like in one go to get as many pictures from as many customers as possible, yeah? And this is not so easy because, of course, it takes a bit to turn the satellite and so on. You have a bunch of site conditions you have to take into account. And so in the end, it becomes a quite complex optimization problem. And if we only get a little bit better, it would, of course, make quite a difference. Then, when we take pictures, typically the raw data is looking like this, yeah? So, I don't know, some people who have an old TV screen at home know that, maybe still. And the reason for that is that we're typically with radar not only taking one picture, but several ones, because for radar you need a big antenna, and we don't have it on the satellite, so we just imitate as if we had a big antenna by taking several pictures while moving. And it turns out that actually, in order to process this data, you can quite well use techniques here from this quantum machine learning area to process them and in the end get the right results and do that better and cheaper and faster than we can do it usually with classic computers. So it's a nice application here. And then on the quantum solvers, we have aerodynamic simulations. And let me go a little bit deeper into that topic here. Yeah, so first, why do we actually have it? Yeah, I mean, in the past, we had everything in wind tunnels. And wind tunnels have several disadvantages to fluid dynamics. So one very simple disadvantage is it is expensive, because if you fly at high altitude with a big airplane, you have in a Reynolds number range, which you cannot simulate so easily. There's the ETW, European Transonic Wind Tunnel, that allows to be in that regime, in that area. But it needs to be cooled down to minus 160 degrees and operate at something like 4 bars, which is expensive. So outside, then all these cars with the liquid nitrogen are standing and pumping it in to keep the low temperature and so on. This is expensive, better to simulate. But this is not the only reason. One bigger reason is actually, almost bigger, it's also important, but one big reason is also you don't in the end have a consistent result. Because if we simulate, we have all of the airplane, all pressures, we can sum it up, we have the forces, everything is nice. Yeah? When we have this, nothing fits together. Yeah? We have a few points where we take pressures. We hope that this is not influencing the flow too much. When we sum up the pressures, we don't get the overall force because of all kinds of uncertainties in there and so on. And the third reason is it's very difficult to put into an optimization loop something that is in a wind tunnel. So if we want to try what is the optimum shape of a wing or just a winglet or whatsoever, this is the way to go, because here it just, in the loop, it takes too long. So what could we do there? Yeah? So 3 years ago, where we were standing, yeah? And what we classically do, yeah, what we normally do is we take a design shape, so something, how should the aircraft look like, what's our wish, how should it be, yeah? And we build a mesh around it. And here we have a lot of decisions to take, yeah? How should this mesh be structured, how should it look like? How does it fit to which equations do we actually want to solve? Actually, I would love to solve the Navier-Stokes equations because everything is in there. Yeah? It would be perfect. The problem is today's classical hardware does not really allow to do that. And hence, we have something with Euler and some turbulence models on top, and there are different ones, and we can connect all these things. Yeah? And then we put some finite volume scheme typically on it. a few others, yeah, we had a discussion on Lattice-Boltzmann already, and we get the airflow around the wing. Now, different, we could do it, design shape, we just take some points, and in the end, we solve the PDEs with a physics-informed neural network. And the cool thing is, then we have all complexity in here, and not in here. In other words, we could, in theory at least, solve Navier-Stokes. And we were very motivated to go there, and we had, by that time, actually still with Pascal, a strong partner on this. And we were looking at this, and here we were at some point coming to the limits. And we were just doing this on simulators yet, yeah? So not on a real hardware. But we were coming to limits because we noticed all the different parameters which we have to decide on here are now actually in here, and we don't know them. And here we have several decades of experience, and here we have not. So we were successful to do it for some very simple cases, solve the advection equation, play a bit around with Berger's equation, and so on. But already Euler's equation, we were running into the many parameters we had to decide on here, and we didn't really find the right ones to tune it. And we are sure there is still a lot possible, yeah? So we're still absolutely sure we're not at the limit, because the longer we try, the better we get. But we certainly need a bit of a way through, yeah, to easier find parameters on that level to have that successful. And dream would be at some point to solve Navier-Stokes, what we were never able to do, and what would enable us to increase accuracy and get into areas, optimize into areas we haven't done this before. And of course, yeah, size matters. This year is getting expensive as well when you really try to optimize around shapes. So when you really try to explore whole landscapes of possible designs, and for one design, it's millions of calculation already, and so for maybe thousands of designs we want to try, it becomes accordingly also expensive when you're simulating. What's the next step? Yeah. So, yes, quantum computing challenges are reaching beyond hardware, no? And this is something I'm very convinced now, and I had a lot of discussions here, so I'm not the only one. I'm quite happy. And of course, multidisciplinary approach is key. But you maybe remember my first slide with the steam airplane, yeah? It will, in the end, probably look a little bit different than we were assuming, and so we're very eager to have new views. But if we solve it, more than 100 years of aviation has taught us we get around all these problems we cannot solve. Yeah, we have a problem like Navier-Stokes, we can't solve it, we found ways around. And we have a lot of these problems in there. Also, we have had here the discussion on SAT problems, yeah, so combinatoric problems and so on, yeah. So in the area of optimization, a lot of these we cannot solve, we found ways around. And now what will happen if we suddenly can solve it? And this is something we actually need to learn, because after working differently for 100 years, we don't yet see these use cases. Thank you.